And we're back at fsharpConf, and
Hello.
I'm here with Evelina.
Hello.
Awesome. I'm really excited that you were able to make it here to Redmond in person.
Oh, thank you. It's exciting to be in the Channel 9 studios.
Yes.
So thanks for having me.
Yeah, we're really excited about your talk. But last time we talked, you lived in Cambridge, and I heard you moved to London.
Yes, because I started working in the Alan Turing Institute, which is the British National Institute for Data Science.
That sounds awesome. So you're a data scientist?
Yes, my official title is a data scientist.
Sounds really interesting. Are there any cool projects that you're going to work on?
Well, next month we are starting a really cool project with the National Air Traffic Control in the UK, where we will be basically automating parts of their training system and putting AI agents into that. So that's going to be a lot of fun.
It sounds really cool.
So be careful if you fly into the UK.
Okay. And your talk title sounds really cool, How to Look Like a Statistician.
Do you want to look like a statistician?
I do. I mean, yeah.
Yeah, so I think you'll switch from the enterprise usage of F# to more like cool uses for functional programming.
Sounds cool. So I'll let you take it away. And
Thank you.
Yep, let's listen to your talk.
So my title is How to Look Like a Statistician, Developer's Guide to Probabilistic Programming. So if you ask someone if they want to look like a statistician, well, am I a statistician? That's a question. As I mentioned, I work as a data scientist in the Alan Turing Institute. And if I ask someone, do they look like a statistician, they probably imagine someone like this. This is actually a famous statistician, Sir Brian Cox. He worked a lot on survival models. But yeah, if you also search how statisticians look like, well, do you want to look like a statistician? Well, have you heard the latest stats joke? Well, probably. The internet vision of a statistician is someone like this. And this is a stock photo of a statistician, and I really like this photo because the guy is wearing a lab coat. Statisticians don't wear a lab coat. And he's actually writing on the screen the other way around. So hopefully after this talk you will know how to look like this guy. So I'll be talking about probabilistic programming. So what is actually probabilistic programming? You have probably heard about probabilities, and probabilistic programming is about creating probabilistic models, which is a huge area of machine learning. So what are probabilistic models? I'll be using a very nice use case where I actually used probabilistic models and data set that I played with, and that's a Stack Overflow developer survey results from 2017. And the data scientists in Stack Overflow were really nice and let others download the data from the Stack Overflow developer survey. So I looked at the data, and when they published the data, there were a lot of articles in the news. Do developers who use spaces make more money than those who use tabs? These were the titles, and it got picked up by major media like BBC, and they ran articles about programmers who use spaces are paid more. I really like the quotes here, by the way, are paid more. So I thought, okay, does it make sense that programmers who use spaces make more money than those who use tabs? So I looked at the data, and this is a salary distribution when you look at the data. And there was a field for people to fill in their salary, and this is the distribution. And you can see that it looks slightly strange. You can see that there are two bumps in the distribution, one in the beginning and one in the middle. So I thought, okay, there is something strange happening. Who are the people who report very low salaries? So I looked at people who report their annual salary lower than $3,000. Which comes to about $250 per month. That's not a huge salary. Well, most developers who reported this salary come from India, which unfortunately may be true because developers in India are probably not paid that well. But the second country that reported very low salaries is actually Poland, and then Russia, and then among the first 10 countries, there's also Germany. And then I thought, okay, there is something really strange happening there, because if developers in Germany report salary of $250 per month, that's not much. That's really weirdly low. So I decided to look at the data in more detail. And this is a distribution from different countries, from France, India, and United Kingdom. And you can see that these distributions have nice big bump in the middle. And then I plotted some of the suspicious countries. So this is the salary distribution in Central and Eastern Europe, coming from Germany, Poland, and Russia. And you can see that these distributions, they look different. For example, the Polish one, there are two nice big bumps. And in the Russian, that's the green one, the first bump is even larger than the second bump. And for Germany, there is one small bump and then a big bump in the middle. So what is happening there? Are there groups of developers that are paid nothing and then a lot of developers that are paid normal salary? Well, what's wrong? Well, my suspicion was that people didn't read the question properly. So this is the actual question as it was presented in the survey. And it asked, what is your current annual salary in local currency? Blah, 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 blah. And even though annual is there highlighted, it's underlined, I thought, okay, maybe people just report their monthly salary because people just don't read questions properly, especially in Eastern Europe, probably. I am actually from the Czech Republic, and my background knowledge is that when people negotiate their salary and talk about how much they are paid, they never talk about their monthly salaries. They always talk only about their monthly salary. So they don't talk about year summaries. And I asked my friends in Poland, and they confirmed the same thing. People don't ever talk about their annual salary. They just ask about their monthly salaries. So, okay, people just looked at the question, saw the word salary, and reported their monthly one, probably. And I will use probabilistic programming in F# to show you how you can actually quantify that and find out what's the real salary and how many people can't read questions. So this is the salary distribution in Poland. And as I said, there are two bumps, and they are almost equally sized. So what can I use to model the data like this? This is my theory that I will try to validate using the data. And I will use something that statisticians call mixture distributions. What is a mixture distribution? Well, it's a distribution that's formed by a mixture of multiple normal or standard distributions. So this is an example of two Gaussians or normal distributions. You can see that they all have one bump and they are centered at different values. And if we do a mixture, we will just multiply them by a certain weight and sum them together. So now this is my mixture distribution where I mixed the two Gaussians with equal weights. I can also change the weights. For example, now the distribution to the right has larger weight and the distribution on the left has smaller weight, and they are about the same height right now. And I can change it as well. I can give one distribution a very small weight and the other distribution a very large weight. So you can see that I can use this to model my two-bump distribution that I had for the developer salaries in Poland. And the only thing that I need to find are the parameters of the distributions and the weights. So now you are, okay, that's a lot of statistics. What is this whole thing about? I will talk about how we can use this in the framework of probabilistic programming. And in probabilistic programming, the main thing is that probability distributions become first-class citizens in the language. And later on, I will show you how functional programming actually creates a very nice framework for this, and how we can basically put in probability distributions and treat them as first-class citizens, as if they were our variables. But first, we need to look at the mixture distributions a bit more formally. So this is how a statistician would write a mixture distribution. There are many Greek letters. So what does this mean? I don't want to go through the Greek letters and see like what are the mu's and sigmas and things like that. If I want to look at it from a developer's perspective, I want to see something that I can understand. And the most straightforward way to interpret something with probability distributions is through sampling. And what is sampling actually? Well, let's look at a very famous problem called the Monty Hall problem. And the Monty Hall problem, it actually comes from a TV competition called Let's Make a Deal. And there are 3 doors in the competition. And people came there dressed in a crazy ways. And they competed to actually win a car, a nice old car like this. So they had 3 doors. And the question is, so the car that you want to win is behind one of the doors. And 2 other doors have something that doesn't have any value. And traditionally, this is a goat. So in the game, you pick one of the doors. And now Monty Hall, whose name is the name of the challenge, and who was the presenter of the competition, asks, okay, so what do you want to do? I will open another door. So Monty Hall opens another door and shows a goat. And now they ask you, do you want to change your selection? Do you want to keep your selection, the door you selected? Do you think the car is behind there? Or do you want to switch to the other door, the unopened one? And normally, the probability that the car is behind the door that you picked originally is 1/3, because there is equal probability. And after opening the door, do you want to switch or not? If you haven't seen this challenge before, then you might think, okay, I should probably, well, it doesn't matter because the probability is still 1/3. Well, we will check that. So after you change or not change the door, Monty Hall opens the other doors and shows another goat and a car. So how can we do this using probabilistic programming? Well, first I will start with normal sampling. This is my F# code to actually do a simulation from the Monty Hall problem. So we'll just create some types. Type for a door that can be either a goat or a car. And the game is just some list of doors. And my strategy is either to stay with the door that I picked originally or to switch to the other door. So these are just my helper functions to generate a game. And I'll just run this and explain it a bit later. So this is my very simple, straightforward function to play the game. So I'll just generate some state of the game, pick a door, and then the host opens the other door that I didn't pick. And if I decide to switch, then I will just choose the other door that the host didn't choose, and I will choose one of them randomly. And then, depending on my strategy, I will just say, okay, did I win or not? The actual code is not that important in this case. So let's have a look at the probabilities. So probability of winning if I stay with the current selection, if I try the game 10 times, is 40%. And the probability if I switch is actually 100%, which is weird. Well, what if I increase the number of samples to 100? Now my probability of winning if I stay with my original selection is 37%, and the probability if I switch the door is 72%. What if we increase the number of samples even more? Let's say to 10,000. Let's have a look. Okay, and now the probability of winning if I stay with my original selection is 34% almost, and if I switch, it's 66%. So you can see that it's getting more towards 1/3 and 2/3. And as I increase the number of samples, it gets more and more precise. And this is something called Monte Carlo sampling. And it's a very common framework in estimating probability distributions. When you want to see the value of a probability distribution, you just sample from it, maybe using a very straightforward sampling like I was using here, or a more complicated schema. And After the sampling, you just pick a large enough number of samples, and this will give you a good estimate of the distributions and probability values. So why should I use functional programming in this, and where does it come into it? Well, the sampling that I was showing you here was very straightforward. The problem is very straightforward. But we can also represent it in a much more interesting way using computation expressions in F#. So here I have my door type that can be either a goat or a car. And now I created a new type for a Monty Hall value, which gives me a door and the probability value for that door. So initially, if I do my original selection, the probabilities are all equal, so both goats and cars get probability of 1/3. And after that, I will get the different values after I change or not change my selection. And now I'll create another type called distribution. That will be a sequence of the Monty Hall values. And here are some helper functions for creating uniform distributions. And now here comes the interesting part with computation expressions. So here I created another type, which will be a probabilistic computation. I will call it a probabilistic computation. And it can be either a sample from the distribution, or it can return a value. So this looks quite complicated. So what does it actually do, or what do I want to use it for? Here I use it to create my probabilistic computation builder, which is the computation expressions. And I'll basically just use the builder to wrap my values in that probabilistic computation type. And my goal with this is to basically just record what kind of selections I am doing in the game. So that when I use my probabilistic computation builder, or when I create a computation expression, and I actually run it on my data, it will record what am I doing in the computation, what kind of distributions I'm going through, because distributions, remember, are the sequences of Monty Hall values, and which door I'm selecting. So, yeah, let's look at the rest of the Monty Hall with computation expressions. So here I created the probabilistic computation called prob. And if you have never worked with computation expressions, for example, async is a computation expression. So I will use it almost the same way as you would use an async. I will just call prob with curly braces. And now you can see that my program is simplified greatly, because now my stay probability or stay scenario, where I just pick an initial door and don't change my selection, will basically just create the initial door distribution, which is a uniform distribution over 2 goats and 1 car. And then I'll just return my selection. And if it contains a car, then I won. And if it contains a goat, then I lost. And my switch strategy is slightly longer, but still much more readable than my original simulation code. So first, I will just pick my initial door. And then if I decide to switch, then I'll just look at the initial door, and if it contains a car, if my original selection was a car, then I want a goat. So I will return the goat. And if I originally selected goat, then Monty Hall opened another door which contained another goat. So that means when I switch, I want a car. And the interesting thing here is that the initial door, that's here, although I created a uniform distribution, now my initial door basically just represents a sample from that distribution. You can see that its type is a door, which is either goat or a car. And my switched door is, again, either a goat or a car. And here I am basically doing pattern match on the initial door, which is a sample from the uniform distribution. So the cool thing here is that I'm working with probability distributions, but I can refer directly to samples that I don't know the value of. So let's actually run this. I have to run everything. And the only thing I had to do is actually wrap it in my computation expression, which is the prob keyword in this case. So what do I do with it now? As I said, my type sample, etc., and return type basically just record what I'm doing and how the computation is processing the values. So here I will basically just enumerate all my options together with their probabilities. And I added some code that will print what I'm doing. And here is another helper function to actually just compute the final probabilities. So if I stay, let's have a look what the code went through. So the code actually went through all the 3 different options that I had in my original distribution. So I could either select a car with probability 33%, or I could select a goat with probability 33%, or I could select the other goat with the same probability. And now my final result is a car with probability 33%, or a goat with probability approximately 67%. So here I got the values of the whole distribution. And what if I switch? So this is what the computation went through. So in the first option, first I selected a car with probability 33%, and after Monty Hall opened another door containing a goat, I decided to switch. So I switched to the other goat. So my first option was a car with 33% probability, but after that, with probability 1, I got a goat. In the other scenario here, my first selection was a goat. Then after Monty Hall opened another door, I decided to switch, so I switched to the car in the other option. So again, 33%, and then with probability 1, the car. And in the last scenario, again, I selected a goat in the first place. Monty Hall opened the other door, showed the other goat, and then I decided to switch, and I won a car with probability 100%. So you can see that my probabilistic computation, the computation expression, actually recorded what choices I made during the game. If I go back to the probabilistic expression, here, first it recorded what was my initial door selection and what was my second selection in the switched door. And then I could just go through the whole computation and all the probability values that it assigned to different scenarios and compose them, do something clever with them. In this case, the probabilities were fairly straightforward, but in a more general case or more complicated cases, the probabilities would be more complicated, and then I would have to do something clever with them. But in this case, it allowed me to just summarize them directly. So let's go back to our mixture distributions. I showed you this equation, which looked fairly complicated. How does it look if we do it more in normal ways, or if we talk about it in a normal voice? So a mixture distribution of a salary is equal to the probability that someone read the question correctly and then multiply it by the actual salary that they reported. Or the other scenario is that someone made a mistake, they didn't read the question properly, and then multiply it by 1/12 of the salary. And this will give me the probability of a reported salary in general. And now you can see that I have just 2 unknown things in this case. So I have the probability that someone can read a question properly and the value of their annual salary. So what can I do with this? As I said, we have just 2 unknown parameters. And this equation, it's really easy to compute if we know the values. If we knew the annual salary and if we knew the probability that someone in Poland can read a question properly, then we can compute the probability that any salary gets reported. How do we actually write that down as a probabilistic computation? Well, this is my pseudocode in F#. I really want to make probability distributions first-class citizens in my language. So this is how I would love to write it. So I would like to just create a salary that will be a Gaussian with some kind of mean and variance. These are the unknown parameters. And then mistake will be just a probability distribution called a Bernoulli distribution, which is just a statistical fancy way of saying a coin toss distribution. So it's just distribution between two values. So what's the probability that someone makes a mistake? And then my observed value will be just, if they made a mistake, then it will be 1/12 of the annual salary. And if they didn't make a mistake, then I will just report the actual salary. So how do we do this with computation expressions? So here I have some helpers first. Let's evaluate them. And now my value is not a goat or a car. Now my unknown values are floating point numbers. And I have two distributions. So instead of the Monty Hall values, which gave me just discrete values of a goat or a car, together with their associated probabilities, I have two distributions. One will be a Gaussian with a mean and variance, and the other will be a Bernoulli probability distribution. And my probabilistic computation type looks exactly the same as I had in my Monty Hall problem. So again, I have a sample, or I have a return value. And the sample basically just records the distribution that I'm going through and the value, and returns another probabilistic computation. And I will use this to create the probabilistic computation builder, my computation expression. So this is exactly the same thing I had in the Monty Hall problem before. And again, the goal is to just record what I'm doing with the probability distributions, because I can do something fancy with them later on. And this is my model for the whole problem. So again, it's wrapped in the prob keyword in this case with curly braces. And the code looks almost the same as I had on my slide. So first, I will take the yearly salary, which is a Gaussian with some mean and some variance. And here you can see that its type is the value, which is just my wrapper around float. So even though I'm assigning it to like Gaussian, which is a probability distribution, it's looking like just a sample from the distribution, just like one value taken from the distribution. Now my Bernoulli distribution for a mistake, the probability that someone made a mistake, is again another value. And what I'm doing here is I'm just checking if someone made a mistake. If the sample distribution from the Bernoulli is 1, then I will return the salary divided by 12, monthly salary. Otherwise, I will just return their annual salary. So again, you can see that this is very readable. You can see exactly what's going on in there. And the cool thing right now is that in the background, I can do anything. I can do some clever things, or I can even do just sampling, because I know how the structure of the computation looks like and what the computation is actually doing behind there. So what I will get out of this is basically samples of salaries and probability if someone made a mistake. And if they made a mistake, then I'll report one thing, and if they didn't, I report the other thing. So what can I do with it? Well, as I said, the mixture distributions and the whole setting of the problem is fairly straightforward. So how do we get the actual parameters of the salaries, like the salary mean, salary variance, and the Bernoulli distribution, the probability that someone made a mistake? How do we actually get the values of the parameters? Well, this is the complicated part. You actually get PhD out of this. These are actually slides from doing something similar for a specific model in my PhD in Cambridge. So this stuff is really complicated. And because this is just a talk on how to do probabilistic programming, the cool thing about probabilistic programming is that you don't need to know any of this. you really don't need to know any of these equations on how to construct them. The only thing, if you are doing probabilistic programming, is you have to know how to specify the problem. And this is it. You just have to pick probability distributions, and the cool thing is it all happens in the background. And you let the author of the library or whatever you are using to figure out this complicated stuff. So I'll be talking about the world's slowest probability inference engine that I created for this talk. So the algorithm that I used is called the complete enumeration, and usually you will find it in any machine learning textbook in the category under the first chapter on how not to do things. So this is my distribution of salaries in Poland. And what I will do, I will try different parameter values, different annual salaries, different means, different variances, and different probabilities that someone made a mistake. So these are just 3 examples here. And what I will do, I will discretize them, because sometimes working with continuous distributions is not that easy. So I will just discretize them. That means I will create bins and calculate how much mass is in each bin. And after this, I'll just compute the difference between the distribution that was observed, meaning the distribution that was reported in the Stack Overflow survey, and my theoretical distribution that I got from certain values of the means and probabilities. And then, after comparing them, I will find basically I'll just pick the closest distribution, the one that looks most like the data that were reported. So let's have a look at the demo, the world's slowest probabilistic inference engine. So here are my helper functions on how to discretize the values. And here I will just basically go through the distributions. And for example, I know that for a Gaussian, most weight is concentrated between 3 standard deviations from the mean. So I will just take my Gaussian distribution, compute the standard deviation, and then basically just iterate through all the values between the distribution, the mean minus 3 standard deviations and mean plus 3 standard deviations. And I'll basically vary all the parameters. As I said, I'll just try different values for the means, different values for the probability that someone made a mistake. And as I said, I'll just work with discretized probabilities. The code is not very interesting, though, to be honest. And here is the interesting thing. Here I'm actually going through the probabilistic computation, the computation expressions that wrapped my choices in the sample or return types. So here I will just basically take the sample of my distribution, and for all the different parameters, discretize everything, and then just enumerate all the possible values. And I'll just compute the histograms for all the possible distributions. I'm going through this code fairly quickly, but the important thing with probabilistic programming is that you really don't need to write this kind of code. The only thing you are interested in writing is the actual model, and then let the engine behind that figure out how to compute everything. And this is my code to actually compute 2 histograms, 2 discretized probability distributions. And now my code to pick the most likely distributions. And I will apply it to Stack Overflow data. I have the data in a CSV file, so I'll just use the CSV type provider and basically just filter out the data that belong to Poland and just the developers that reported their salary. Now I got just 317 values, which is not that much. And the average reported salary is almost $21,000 per year. And the maximum reported salary one lucky guy in Poland is basically paid $110,000 a month, or a year, sorry. So now, actually, I will run my slowest probabilistic inference engine and find the most likely distribution that created the values that I saw in the histogram. So, and it ran fairly quickly. So actually, the distribution that created the values had a mean of $28,400 per year. And the interesting thing is that my probability distribution for the mistake value is 0.25. That means 25% of developers in Poland, I'm sorry, can't read questions properly. I'm sorry to all my friends in Poland, but 25% of the people just don't read questions properly in Poland. So this is my estimated distribution. This is how it looks when I actually plot it. So you can see that it basically estimated a nice two-bump distribution. One is the distribution for the people who actually made a mistake, and the other is for the people who didn't make a mistake. And as I said, the cool thing about probabilistic programming is that you don't really have to care about how it's done in the background. In the real world, there are two types of probabilistic programming languages. One type is more procedural, where, for example, in Stan, you specify your model in a very similar way that I specified it here in F#, and then it gets compiled into C++, and then you run the compiled program. And then the other type of probabilistic languages is where, for example, Anglican, which is a nice functional probabilistic programming language in Clojure, where, again, you specify the program in a very similar way that I used, and then they just do very clever things with it in the background, either sampling or what you can use this kind of structure for when you actually create the program and report what's happening there and how the computation is progressing. You can differentiate the program and then take the derivative of the program and do some cool stuff with that. But as I said, the cool thing is you don't have to care about that. That's something for the authors of the probabilistic programming language or library to figure out. So this is the end of my talk. You can ping me on Twitter on Evelgap, and I also have a blog at evelinag.com. And if you are interested in probabilistic programming, probably use computation expressions, because that's a very nice way to actually hide all the complexity that's behind there and just take the computation and do cool stuff with it. Thank you.
Yeah, hello.
Oh, hello, Philip.
Hi. I am here to facilitate Q&A.
Thank you.
I think my mic is on, should be good. Let's go here, let's see if we got some questions. Well, it wasn't really a question, but we did get a statement on Twitter about saying they're halfway through this great talk about probabilistic programming using F#, and some pictures of empty pizza boxes.
That's great. That's great to hear that people are actually enjoying that.
So maybe
I suppose that's people from Europe who are just relaxing somewhere with a beer in their hand and pizza.
Maybe there's something that could be done in a future version of this talk about probability of how much pizza you think you're going to eat over a period of time, and if you've maybe misread the question or something like that.
Yeah. Or if people reported their pizza consumption in kilograms or ounces.
Yes, and then the survey respondent just takes those as raw numbers and says, well, this is the amount of pizza, unitless, if you will. So there were quite a few insights here. I think my favorite was definitely the people are probably not reading the question correctly when they're reporting salary information.
Yes. Well, that's actually an interesting part of being a data scientist, because sometimes you have to deal with people just not behaving the way you expect them to, because the people come into play as well. And sometimes you just look at the raw data and do some conclusions from there, and then it doesn't make sense.
Interesting. So one thing that I really liked was I really liked representing sort of this complex stuff in the form of a computation expression, because well, I took calculus and differential equations, but that was a long time ago in college. I can't really read that anymore, but I can read computation expressions. So I'm kind of curious, like, what are some of the things that go really well? What are some things that go well and things that may not go so well if you want to try to model this with computation expressions or something else in F#? Because I'm kind of curious, because this looked great, but I'm curious if there are other things where it's like, oh, maybe a different approach in the language might be better. I guess I don't really know what that would look like.
Well, the cool thing with this kind of computation expression is that it basically just records what you are doing there.
Mm-hmm.
Because some people, for example, like monads and things like that, this is not a monad, my computation expression here, because the types don't really match, and the only thing it's doing is basically just recording what we are doing in the computation. Mm-hmm. And then you can take that and do anything with that.
Right. So your goal is not necessarily like composing this and this and this and this and this or something like that, just more of like a nice way to represent the work and then do something with that representation later.
Yes.
Okay, I see.
I know there are some papers on basically using monads to represent probability distributions, but that's usually not how probabilistic computation or probabilistic languages work, because they want to do multiple different cool things in the background, whereas in monads, for example, there are monads that use composition to compute the probabilities, the resulting probabilities. Mm-hmm. But that's not how you do it in practice, because that gets very complex very quickly. Mm-hmm. So normally you just record that and then use some kind of optimization engine in the background.
Okay, cool. Yeah, that's great. Mm-hmm. So we have a question there. Why not use R for statistics?
Why not use R for statistics? Well, that's a fair question. The thing is, for example, there are not that many probabilistic languages in R either. The thing you can do in R, for example, if you have a more complex problem than I had here, is you basically specify your program in like a Stan language, and then you compile it from R, and then you can use the compiled model from R again. Mm-hmm. But this doesn't actually give you much advantage. Mm-hmm. And the thing is, R is not very efficient, to be honest. Mm-hmm. So usually whenever you have anything efficient in R, it's using some other inference engine in the background. But from R, mostly people, if they use probabilistic programming, they use Stan, which, as I said, you don't actually specify even the model in R, you specify it in the Stan language.
I see.
Which basically the model specification looks very much like this, basically. You specify some probability distributions, and then you operate with their values in some way. Mm-hmm.
Would you say that R for something like this might be useful to like prototype something really quickly in R?
Yes, you can do that, but depends on what you are doing.
I see. You think it might just be a lot of work to like translate the thing that you built into something that's actually going to run decently?
Yes, that's always the question. Mm-hmm. But with something like this, here I chose, for example, a Gaussian distribution because that's the simplest to use usually. Mm-hmm. You can use different distributions, for example, a gamma distribution, but even the Gaussian works pretty well. So this is, as I said, this is a very slow inference engine that I had in the background. Mm-hmm. So this is more sort of for a demo purpose. Mm-hmm.
I see. So there's ways that you could write it to make it much more efficient. Okay, cool. The code might not look as nice.
Yes.
That's how it always goes.
I just thought this is a very cool way to represent probabilistic computation.
Yeah, I really like it. I think that's fantastic. So what are some? Oh, looks like we're out of time here. I was going to ask one more question.
No, I want to talk about statistics.
But Evelina, I guess you could sort of mention like where you are on GitHub, Twitter, that sort of stuff.
Yes. Just ping me on evelgap on Twitter, or just find me on Twitter or on GitHub anywhere. I think I'm the only person in the world with my name, so just Google me.
Very easy to find. Excellent. So next up, we're going to have Odi from Lagos, Nigeria, speaking with Tomas about how he came into F#, just learning the language and kind of transitioned over the course of a year from being an absolute beginner to making a contribution to the compiler. So that should be a very interesting discussion.
Thank you.
Thanks.